Hello everyone, welcome back to my channel InfoSec Lab. Today we're going to continue our series of TryHackMe's web app pen testing, and the topic is going to be DOM-based attacks. DOM-based attacks is a vulnerability that allows attackers to target the document object model, which is DOM, meaning that they can manipulate what user sees and take over the browsers. Throughout this room, you get an understanding of what the DOM is, understand modern front-end frameworks, and we're gonna learn about different types of DOM-based attacks. Especially, we're gonna dive deep into DOM-based XSS, which is a very common vulnerability in a web application. Last but not least, we're gonna be presented with a vulnerable applications where we can assess our skill on DOM-based attacks. Now, without further ado, let's get started. Before we can dive into the DOM-based attacks, we need to explain what the DOM is. DOM refers to Document Object Model, which is a programming interface that displays the web document. When you make a request to a web application, the HTML in the response is loaded as a DOM in the browser. In essence, the DOM is a programmatic view of the web application that the user sees in the browsers. Once loaded, JavaScript can interface with the DOM and make updates to change what the user sees. The DOM has tree-like structure, allowing developers to use JavaScript code to search it or modify specific elements. Let's take a look at a practical example. Here we have a basic HTML file. What I'm gonna do is copy this one and create a file right here. And I'm going to open that in the browser. The document element is always the head of the tree. The substrate HTML is where all the HTML code on the loaded web page would live, which is divided into the head and the body. You can view the DOM using your web browser's built-in developers tools by right-clicking the page and select the inspect option. Okay, so here's the application. Let's do this. We're gonna be inspecting this. To make it easier, I open that in a separate window. As you can see right here, this is the HTML file, and within that is the head section and the body sections. And here's the content of this is the header, and this is the paragraph with the text, the earth says hello. Using the developer tools, we can interface with the JavaScript console and use this to modify the DOM. For example, we could create a new element in the DOM using the following instructions. First, we're going to be opening the console button, and then create a paragraph. Then we create a new text node, and then add a text node into the newly created paragraph. Next, we find the existing paragraph and append the new paragraph to that existing one. Lastly, you'll see the text appear on the website. So let's try that. We're gonna open the console, which is this one, and first we're going to create a paragraph element, which is called paragraph equals document dot create. The paragraph is a P. Now, of course, you can copy and paste the code into the console, but you're not going to be learning anything by doing so. So I would suggest you type it out because it helps you remember what you type. Okay, we also have const data equals to document dot create text node, and then over here we're gonna have the text. Let's just say hello from InfoSec Lab. Next, we're going to be append this text into the paragraph. We can do that by using this function paragraph dot append child, and then now let's select the existing paragraph, which can be done by the function dot get elements by tag name. And within this one, I'm gonna be selecting the paragraph. In this case, because there's only one paragraph in the document, we can actually select index 0, which is this one. You can see it's been highlighted right here. Okay, now we have selected this one. What we're going to be doing is to append a child to that one. And what do we append? The newly created paragraph. So we're going to be using the same method, append child. And it's going to be paragraph. Boom. And you see the text appear on the website right here. This is how you modify the DOM to manipulate what user sees on the website. This is also where the true power of the DOM-based attack lies. If we can inject into the DOM, we can alter what the user sees, or even potentially take actions as the user, effectively impersonating them. This became a significantly larger problem with modern web application frameworks, also called the single-page web applications, where control over the DOM does not just mean control over a single page, but persistence across the entire web application. Answer the questions. What does the DOM stand for? Document Object Model. What JavaScript command can be used to create a new HTML element is create elements. What JavaScript command can be used to get the cookie values from the DOM? It's going to be document.cookie. Modern front-end frameworks. Back in the old days, conventional web applications were built where the responses to each web request would refresh the entire DOM, as shown in the example below. So every time you request a new page, the server will send back a response and the DOM will be refreshed entirely. The response provided to the web request would be provided complete new HTML code, and the DOM would be rebuilt from scratch. However, this was quite cumbersome and decreased the responsiveness of applications. The rise of the modern terms. With the rise of the modern front-end frameworks, birth was given to a new web applications model called the single-page application, or SPA. SPAs are loaded only once when the user first visits the websites, and all code is loaded into the DOM. Leveraging JavaScript, instead of reloading the DOM with each request, the responses only contain the data required to update the DOM. This drastically reduces the amount of overhead with each request, and while the initial load of the application might take longer, it is much more responsive when being used. Modern front-end frameworks such as Angular, React, and Vue allow developers to create these SPAs. Instead of the web server being responsible for the DOM as well, the SPA is loaded once and then interfaces with the web server through API request. While this increases the responsiveness of the application, it can lead to interesting misconfigurations and vulnerabilities. The most two common are discussed below. The first common mistake is confusing the security boundary sets. There is a common saying in application security that states, client-side controls are only user experience. All security controls must be implemented on the server side. This is important because a threat actor can control everything in the browser and thus can be bypassed. Not understanding this principle most commonly leads to authorization bypasses. An example of this is when the developers disable the edit button in JavaScript. However, since you can alter the DOM in your browser, you can re-enable the button and make the request, thus leading to an authorization bypass. While it creates a better user experience to have a button disabled, a server-side security check is still needed to ensure that the user making the request has the relevant permissions to perform the edit actions. Second issue is the insufficient user input validation. This often happens when the front-end and the back-end development teams do not communicate who is taking responsibility for certain security controls. The front-end team will often implement features to sanitize or validate user input before it is sent to a request to the web server. However, as mentioned before, threat actors can bypass front-end controls. Therefore, the front-end team should ensure that the back-end team performs the same input validation and sanitization when the data is sent in the request. However, because the back-end team usually does not know exactly how the front-end works, they are more likely to send raw, unsanitized, and unfiltered data to the front-end in responses, expecting the front-end team to perform just sanitizations on the data before displaying it in the application. It can often lead to no team taking responsibility for input validation. As each team expects the other team to deal with security, it can often create security gaps, allowing attacks such as cross-site scripting or cross-site request forgery. This problem is compounded into the modern age, where most applications no longer work in isolation, but are heavily integrated with other applications and systems. While unsanitized data injected into application A may be harmless to application A, the developers of application B might incorrectly assume that this data has been sanitized, leading to a vulnerability in application B through data sent by application A. So answer the question, what does SPA stand for? That's single page application. Should security be implemented client-side or server-side? Server-side. Well, technically it should be both, but in this case, the answer is server-side. The control can be implemented to ensure that bad user data does not make its way through its input validation. DOM-based attacks. With our background information complete, we can finally look at the DOM-based attacks. In the previous task, it was mentioned that client-side security controls are only for the user experience. However, with the rise of the modern front-end frameworks application, this rule no longer holds true. Ignoring client-side security controls is exactly what leads to DOM-based attacks. The blind server side. While there are many different DOM-based attacks, all of them can be summarized by insufficiently validating and sanitizing user input before using it in JavaScript, which will alter the DOM. In modern web applications, developers will implement functions that alter the DOM without making any new requests to the web server or API. For example, a user clicks on a tab in the navigation pane. As the data on this tab has already been loaded through API request, the user is navigated to a new tab by altering the DOM to set which tab is visible. A second example is a user filters the results shown in the fit table. As all results have been already loaded, through JavaScript, the existing dataset is reduced and reloaded into the DOM to be displayed to the user. In these examples and many other actions, no requests are made to the API, as there is no need to refresh the data being shown to the user. However, this leads to an interesting issue. What will protect us now if all of our security controls for data validations and sanitization were implemented server-side? Therefore, with the rise of modern web applications, client-side security controls have become a lot more important. The source and sink. As mentioned before, all DOM-based attacks start with untrusted user input, making its way to JavaScript that modifies the DOM. To simplify the detection of these issues, we refer to them as sources and sinks. A source is the location where untrusted data is provided by the user to a JavaScript function, and the sink is the location where the data is used in JavaScript to update the DOM. If there's no sanitization or validation performed on the data between the source and sink, it can lead to a DOM-based attack. Let's reuse the two examples above to define the sources and sink. The first example is the user clicking on a new tab on the navigation panel. When this happens, a developer may update the URL with a pound sign and the tab name to indicate the tab that the user currently has active. The sink is going to be a JavaScript function executes on the event that the URL has been updated, recovers the updated tab information, and displays the correct tab. In the second example, where user filters the results of the table, the source is the input provided in a text box by the user to use to filter the results, and the sink is a JavaScript function that executes on the event that information within the text box updates, and uses the information provided in the text box to filter the data. The first example is quite interesting. Even though the initial user input is a mouse click, this was translated by the developers in an update to the URL. Using the pound sign operator, the URL is common practice and is referred to as a fragment. Using the pound operator in the URL is common practice and is referred to as a fragment. Have you ever read a blog post, decided to send the URL to a friend, and when they open the link, it opened at exactly the point where you were reading? This occurs because JavaScript code updates the pound portion of the URL as you are reading the article to indicate the heading closest to where you are at that article. When you send the URL, this information is also sent, and once the blog post is loaded, JavaScript recovers this information and automatically scrolls to the page of your location. In our example, if you were to send the link to someone, once they open it, they would view the same tab as you did when you create the link. While this is great for user experience, it could lead to a DOM-based attacks without proper validations of data injected into URL. With this in mind, let's take a look at DOM-based attack example. The DOM-based open redirection. Let's say that the front-end developers are using information from the pound value to determine the location of navigation stuff for the application. This can lead to a DOM-based open redirect. Let's take a look at an example in the JavaScript code, which is this one. The source in the example is going to be the location /hash.slice parameter, which will check the first pound element in the URL without sanitization. This value is directly set in the location of the DOM, which is a sink. We can construct the following URL to exploit the issue. So this is the payload. Once the DOM loads, the JavaScript will recover the pound value https attacker.com and perform a redirect to our malicious website. This is quite a temp example. While there are other examples as well, the one we care about is DOM-based XSS. There are other types of DOM-based attacks, but the principle for all these remain the same, where user input is used directly in JavaScript element without sanitization or validation, allowing threat actors to control a part of the DOM. Answer the questions. What do we call the locations where untrusted user input made its way to the data pipeline? That's the source. And what do we call the function where untrusted user input is reflected back to the application, leading to a successful attack? That's sync. DOM-based XSS. DOM-based XSS is a subsection of DOM-based attacks. However, it is the most potent form of DOM-based attack, as it allows you to inject JavaScript code and take full control of the browser. As with all DOM-based attacks, we need a source and a sink to perform the attack. The most common source for DOM-based XSS is the URL, and more specifically, URL fragments, which are accessed through the window.location source. This is because we have the ability to grab a link with malicious fragments to send to users. In most cases, fragments are not interpreted by the web server but reflected in the response, leading to DOM-based XSS. However, it should be noted that most modern web browsers will perform URL encoding on the data, which can prevent the attack. This has led to a decrease in the prevalence of this attack through the URL as a source. So let's take a look at an example where fragment in the URL can lead to a source. DOM-based XSS jQuery. Continuing our web page location example, let's take a look at the following jQuery example to navigate to the page to the last view of location. Since the hash value is a source and we have access to, we can inject an XSS payload into the jQuery selected sink. For example, if we were able to set the URLs as follow. So this is the payload. However, this will only allow us to XSS ourselves. To perform XSS on our user, we need to find a way to trigger the hash change function automatically. The simplest option would be to leverage an iframe to deliver our payload. So over here we have an iframe. The source is going to be the website, the target website with the pound size, and once click on that one, on load, when the iframe loads, it's going to trigger this JavaScript function right here. And once the website is loaded, the source value is updated to now include our XSS payload, triggering the hash change function, and thus our XSS payload. This is one example of how XSS can be performed. However, several other sinks could be used. This includes normal JavaScript sinks and framework-specific ones, such as those for jQuery and Angular. For a complete list of the available sinks, you can visit this page. Let's take a look at this one. So this is a page from ProxWiki, which is a very good resource for you to learn web application. In the future, I'm going to be creating videos about these labs, but for now, you can just read it for references. Now, going back to TryHackMe. As shown above, the tricky part lies in the weaponizations of DOM-based XSS. Without proper weaponizations, we are simply performing XSS on ourselves, which has no value. This is a key issue with DOM-based XSS. Luckily, weaponizing can be performed through a conventional XSS channels. So what's the difference between a DOM-based XSS and a conventional XSS? When you are looking for XSS, while it may seem to be normal store or reflected XSS, in some cases, it may actually be stored or reflected DOM-based XSS. The key difference is where the sink resides. If the untrusted user data is already injected into the sink server side and the response contains the payload, then it is conventional XSS. However, if the DOM is fully loaded and then receives untrusted user data that is loaded through JavaScript, it is DOM-based. While there might not be a difference in the exploitations of XSS, there is a difference in how the XSS should be remediated. In the former, server-side HTML entity encoding should be used. However, in the latter, a deeper investigation into the exact JavaScript function that loads the data is required. In most cases, a different function should be used. Answer the question. What was the most common source of DOM-based attacks? It's URL fragment. What control implemented by the modern browsers prevent us from using this source? It's going to be URL encoding. Task number 6. XSS Weaponization. To weaponize DOM-based XSS, we need to rely on two conventional delivery methods of XSS payloads, namely storage and reflection. This is why DOM-based XSS, and other DOM-based attacks for the matter, are so hard to exploit. Without a proper delivery method, you are performing the attack on yourself and not a target. To counter this, we either need a web server to store our payload for late delivery or to deliver the payload through reflection. At this point, our DOM-based XSS becomes a store or reflected XSS attack. This room expects you to already understand the fundamental of XSS and its different forms. If you need a refresher, you can take a look at this room, which is the XSS room. Right here, as mentioned in the previous task, reflected XSS, especially when the source is the URL, can become tricky as modern browsers perform URL encoding. This generally leaves us with store XSS as a delivery mechanism. However, this also opens up several additional sources for us. If we perform XSS through store user data, we need to find a sink where this data is landed without sanitizations or validation. General weaponization guidelines. Before we take a look at the case study, it's worth first talking about general XSS weaponization. Oftentimes, you'll find that it is easy to get a combated alert XSS payload to work. But this is usually where the fun ends, and if we're being honest, we haven't really shown any impact. The next crutch that is often used is to attempt to steal users' cookie. However, this quickly becomes a problem when cookie security is enforced by using the HTTP-only flag, disallowing JavaScript from recovering the cookie value. We need to dive deeper to weaponize the XSS vulnerability to achieve a valid exploit and show the true impact of what was found. The following is a great article that talks about XSS weaponization. And if you have time, I would suggest you spend some time reading this. It's very helpful. It helps you learn a lot about XSS. To fully weaponize XSS, we first need to realize the power of what we have. At the point where we can fully execute XSS and load a staged payload, we can control the user's browser. This means we can interface with web applications as the user would. We don't need to pop an alert or steal user's cookie. We can instruct the browser to request on our behalf of the user. This is what makes XSS so powerful. Even if you find XSS on a page where there isn't really anything sensitive, you can instruct the browser to recover information from other, more sensitive pages, or to perform state-changing actions on behalf of users. All we need to do is understand the application's functionalities and tailor our XSS payload to leverage and use this functionality to our advantage. So let's take a look at the case study. In 2010, it was discovered that Twitter, or X, has a DOM-based XSS vulnerability. In an update to the JavaScript, Twitter introduced the following function. We search for the power exclamation part in the URL and assign the content to the window.location object, creating both a source and a sink with the proper data validations and sanitization. As such, an attacker could get the coveted pop simply using this payload right here. As I mentioned before, this wouldn't really do anything. However, the issue was weaponized by threat actors. The vulnerability was weaponized using the on-mouse over JavaScript function to create a worm that would retweet itself to further spread the new users. Redirect users to other websites, in some cases containing further malicious payload, display pop-up, and other intrusive behaviors that could potentially fish for personal information. In the end, the weaponized exploit affected thousands of users. It is worth remembering that this was 2010. If such a bug were found today, the impact would be even larger. Answer the questions. What flag prevents JavaScript from getting access to cookie value? HTTP only. What security control that limits the way the content can be loaded makes it hard to weaponize XSS? Now, to answer this question, you have to read this article right here, and the answer is going to be content security policy. Okay, let's get to the challenge. Now that you understand the DOM-based attack, more specifically the DOM-based XSS, it is time to put our knowledge to the test. We gotta start the machine, which I've already done so. While we wait, we're gonna be continuing our reading. You can navigate to the list TryHackMe on port 5173. Here, you'll find a simple birthday list application that's vulnerable to a stored DOM-based XSS. While you can add and update birthdays, you cannot delete them. You aim to weaponize the XSS vulnerability to recover the information required to delete the birthdays. Once you delete all of them, you get a flag. So the goal is to delete all the birthdays. Okay, enumeration. In order to do this challenge and answer the question, you need to analyze the view application. Navigating to application, you see the following one. If you simply use view page source, it doesn't really help. Okay. However, the browser will actually rebuild the view application for us in the debugger. You can access the debugger by right-clicking, selecting Inspect, and then clicking the debugger tab. You see the following one. In the debugger tool, we're gonna see the structures of the files, and we're gonna be using the files in source components folder. And with the files we have alert.view, birthdays.view, and the ping.view. Okay. You're gonna have to use this feature to solve the challenge and answer the question. Hint: you need to trick another application user into giving you sensitive information. However, if you alert this user, they will become suspicious and simply stop using the application. You can cancel them by either logging while you perform the test or restarting the entire machine. Furthermore, if you are able to get an interaction from the user, but it isn't exactly what you were hoping for, perhaps the answer is to monitor the user closer and for longer. Okay, let's get started. I'm gonna enlarge the window right here. In the meantime, I'm gonna add this one to the host file. Since we are doing root, we don't have to use a sudo. Now let's go to the website. It's going to be http list.tryhackme.log and 5173. Okay, so this is the application, and we can go to debugger inspect, debugger source, and we have the files right here. Now it's gonna be a little bit hard for us to read the files right here, so what I'll be doing is copy this one and open it in a new tab, paste it. The same for the birthdays.view. Copy the source URI, paste it here, and last the ping.view. So it looks like these files are the most important files in the application. Alright, so let's take a look at the alert. What do we have? We have context source alert, key, view, update render mode, update. There isn't really anything much to see. How about the birthday.views? Okay, so we have the constant SF main. Oh, looks like we have something. We have data return active at birthday model. Okay, edit model. Sorry, I should have explored the application's functionality first. So let's try adding the birthday right here. There are two fields, so let's test for the XSS vulnerability. This one is going to be person. And this one is to be day. We don't know which one is vulnerable. Okay, looks like the person field is vulnerable to XSS. It looks suspicious to user, right? We don't want that. So what we're gonna be doing is to add a real name in front of that. John Smith. Now by doing this and this one out, I know it's not vulnerable, so I'll just change to a regular birthday. Okay, you can see it right here. Even though the payload says here is stealthy to users, nobody knows about that unless they actually click on the updates and they can see this one. So now we have the add birthday model. We also have the update model. Let's go back to the birthdays.views. So we have alert, we have add birthday, we have payload right here. Okay, we have an API endpoint on port 5001. Let's take a look at what it is. Okay, so this is a list of all the birthday persons. We have the birthday, the gift ID, and the person's name. Good, let's document this. This is the endpoint where we get the, I'll make it bigger. Okay, what do we have next? We have the get birthdays, which is this API endpoints. Well done. What do we have? If the birthdays length equals 0, meaning that there's no birthdays left, we gonna be running this ping one to receive the flag. Okay, so for now we can actually ignore this one because it's just only a way for us to retrieve the flag. So let's just ignore it for now. Console, not quite yet. This one more items you need to receive. Okay, so this one not quite this yet. Once there are no more items, you will receive the flag. So this is an if-else statement where it checks for the length of the birthdays. If there's no birthday left, then we'll be able to get a flag. Otherwise, it's going to display us this message. It's telling that we have to delete everything. Header reset, header submit with the payload right here. This person, okay. Handle delete birthday. We have removed birthday ID. Okay, let's take a look at this. What do we have? Secret is equal to, okay. Looks like in order to delete a user, we need two things. One is the birthday ID and second one is the secret. And here, in this case, secret is achieved through the local storage. Get secret. So let's try interact with the application. Let's see what it does. The console local store dot get item. Let's see. Secret. Oh, it's typo. My bad. My bad. Not the real secret. Another way to check for it is I go to application tab over here. Yeah. Oh no, storage tab, my bad. Local storage, click on this one and you're gonna see the secret key and the value is not the real secret. Okay, let's try deleting one, see what happens. We're gonna be copy this one. Birthday ID. Secret is we'll copy this one. Go here. No, it should be here. My bad. And the secret is gonna be not the real secret. Let's try that. We can try on the console right here. Fetch HTTP list. I can just copy and paste. Okay, I have to allow pasting first. Okay. So we're gonna be using fetch and then script, and the method is going to be delete. Let's take a look at it one more time. So delete path, yes. Redirected false. What do we have? False content application headers. Methods not allowed. Okay, we have methods not allowed. Just get back. So we can see right here, we cannot delete the flag. Okay. Alright, so I get the idea. The reason we cannot delete a person is because we don't have the secret values. And because of that, it's hard for us to actually delete it. We have to get the secret values maybe from the admin of the application to delete these birthdays. But how do we do that? We're gonna be leverage the XSS vulnerability in this application, which is on the person's field right here, and we inject a payload that will steal on the user's cookie section, which is the secret values. How do we do that? First, we're gonna set up a listener on our end, which is on our server. Second, we're gonna be inject a payload that keeps listening for other requests which contains the real secret value. And once we obtain that secret value, we can actually delete the user. So let's try that one by one. Okay, first we're gonna set up the listener on our server, which is Python 3 HTTP server. Once we set it up, let's go through some basic functions. The very first one is fetch. So what it does is to make a request to our server, and our server is HTTP 10.10, my bad, 10.10.121.95 on port 8000. So you can see right here on the left side on the terminal, it shows that a request was made to the server. Similarly, we're gonna fetch a request, but this time we're going to include a parameter, secret equals, and we're gonna get the same thing, which is right here, the secret equals. This is how we listen on the targeted applications to listen to other users' requests to steal the values. How do we do that? We're gonna be using another function, which is when you local storage dot get item, and we need to specify the key name, which is secret, and it shows you the values right here. We're gonna be incorporate this one into the fetch request plus local storage get item. Oh, there's a typo. Here on the terminal, you'll see that we see not the real secret value, which is our own value. We don't need that. But with same concept, we can actually use this function to obtain all the user's values. And here, let's create our payload. We're going to be using the image source is going to be 1 on error. We trigger the JavaScript. Here, the function we're going to be using is the set interval, which repeats the operations for every set amount of time. In this case, set interval. The first part is going to be the function, and the second part is going to be the time. In this case, I'll specify 5,000 milliseconds, which is 5 seconds. Basically, what it means is you'll be using this particular function, fetch function right here, every 5 times. Once every 5 seconds. Over here, we're going to have a function, and we're going to fetch this one. Copy. Functions right here, fetch right here, and the method is going to be get. Alright, so let's double check one of payload one more time. It should work. Image type, we have the source, so we have the set interval. This is the error function that execute the JavaScript function. Secret local storage get item get method gets. Alright, we're gonna copy this one, inject into the source, which is the name field, the person's name field. Submit. And now we're just gonna have to wait on our listener. Yes, you can see it's running right now. Right now, it's just our not the real secret, which is our own value secret. But eventually, there's gonna be other users who get on the application, and their values would be retrieved. There we go. right here. This is the super secret value. Let's copy this one. Okay, now we get the value. Let's update it. We from the console. The virtual machine is so slow. Let's go to the storage, local storage. Click on the website, and now we're gonna double click on this one, expand this one. Now over here, we're gonna change the value to the new one. Save it. Refresh the page, and right now, I believe we should be able to delete all the birthdays. Let's try that. Delete. No. Hopefully, it's just the VM's being slow. Okay. It wasn't updated. Now we can delete it. Yes. Birthday removed. Removed. And now we can actually get a flag on port 5001. My God. The virtual machine is so annoying. My God. Well done. Here's a flag. There we go. What is the source field name that makes the application vulnerable to XSS? Person. What is the sync view directive that makes the application vulnerable to XSS? Let's take a look at it. I know where it is. I mean, we know where it is. We just didn't know the name of the sync. $51.73. Oh my God. Inspected. Ugh. Just bear with me. The VM is so annoying. We have the pink view is. This is a template. We have a template right here. We have a class button at birthday. Oh, we have right here. The person right here, the birthday. So this is where the user's information is displayed on the web applications. And I believe this is the sync, the v-html. So copy, yep, that's the one. Conclusion, defenses. To defend against DOM-based attacks, it is important to once again treat all user input as unsafe, even when it is just being processed by the browser. SAS and DAS tooling can also be scanned. It can also scan code, requests and responses for potential sources and sinks where sanitizations and validations have not been implemented. Okay. So that's it for the room today. I hope you learned a lot about DOM-based attacks and how to exploit this vulnerability in modern web application, especially the DOM-based XSS. If you have any questions, feel free to reach out to me or leave a comment. Thank you very much, and I'll see you next time. Bye.